Okay, I'm now going to go through with you the PowerPoint that talks about reactions and solutions, and in particular we'll be talking about reactions in aqueous solution. That means reactions in which the solvent is water. So first I want to define what a solution is for you. I like to define it using an equation. A solution is simply going to be solute plus solvent. And what we do is we say that the solute is dissolved in the solvent to make the solution. And in an aqueous solution, the solvent's always water. And the solvent is whatever is present in largest amount. And there's some weird kind of solutions that you can think about. Air is a solution. And in air, the solvent is nitrogen gas. And there's a lot of different solutes. One of them is oxygen gas. Another one's argon gas. And carbon dioxide gas. There are several others as well. But because nitrogen is present in the largest amount, that would be 78% nitrogen. And oxygen is present at about 21%. Because nitrogen is present in the largest amount, we say that that's the solvent. And then these that are present in lesser amounts are called the solutes. Again, in this chapter and in most of what we're going to be doing in this course, the solvent is going to be water, and we call that an aqueous solution. All right, I want to discuss with you a little bit about how water dissolves various items. And first, to sort of understand this, we're going to look at the water molecule, which is actually a bent molecule. And we need to understand that the oxygen atom on the water molecule is slightly negative. And we write that with this little Greek delta. Capital delta looks like that. A small delta looks like a squiggly S. And this means partially negative. So this is not a full-blown negative charge that resides on the oxygen. It's a partial one. And then the hydrogens are partially positive. You should probably put twice delta minus because overall the water molecule is neutral. And it turns out we can think about the oxygen as having a charge of about negative 0.4, and we can think of the hydrogens as each having a charge of positive 0.2. And this picture of the water molecule is going to help us understand how, say, sodium chloride dissolves in water. Because if we imagine sodium chloride as being comprised of alternating sodium ions and chloride ions all throughout the sodium ion crystal. And you can see this, actually this picture of water is on slide 3 of the PowerPoint, and a picture of the sodium chloride crystal is on page slide 4 of the PowerPoint. And in that PowerPoint, you'll notice that the chloride ions are green spheres and the sodium ions are blue spheres. And off to the side of the overall sodium chloride structure, you'll see in large circles, you'll see a blue sphere that's surrounded by water molecules. About 6 of them. 1, 2, 3, 4, 5, maybe 5. And then you'll see a green chloride ion surrounded by some water molecules as well. And what you should notice is that with the sodium ion, the portion of the water molecule that's attracted to the sodium ion is going to be negative. Because opposites attract. We know that from the law of electric charge. And you'll also notice in the blue sphere, that's surrounded by the positive parts of the water molecule, the hydrogen atoms. And so what happens is when a water molecule interacts with a sodium chloride crystal, the positive, partially positive hydrogens, they sort of attract the negative chloride ions and they pull them into solution. And then that chloride ion is completely surrounded by water molecules. In a similar but opposite charge way, the negative oxygen on a water molecule, that yanks on the positive sodium ions in a sodium chloride crystal, and all of these negative, partially negative oxygens on the water molecule, they coax the positive sodium ion into solution. And then the sodium ion will be surrounded by water molecules, and those water molecules will have their negative oxygen portion pointing towards the sodium ion when it's dissolved in water. Okay. Now when substances dissolve in water, sometimes they conduct electricity, and sometimes they don't. And I want to go over a few experiments with you to sort of demonstrate the difference between these substances that do and do not conduct electricity when they're dissolved in water. So let's first just define an electrolyte. This is a substance that conducts electricity when dissolved in water. And then a non-electrolyte, well, that should make sense. If this is something that conducts electricity when it's dissolved in water, a non-electrolyte should be something that does not conduct electricity when dissolved in water. So a non-electrolyte does not conduct electricity when dissolved in water. So let me do some experiments for you here real quick. All right, in this jug I have some deionized water. So this is water that's been specially treated. It's been sent through a deionizer here in the science building. And basically the deionizer takes almost all the ions out. What I have here is a little tester. And this tester, what it does, it's got a battery attached to a beeper and two electrodes. And if electricity can pass between these two electrodes, we'll hear a beep. So I'm going to place these electrodes into some pure water. I don't hear anything. So what we're seeing is that pure water doesn't conduct electricity very well. That's contrary to popular belief. People usually think that that water conducts electricity quite well. And it does as long as there are electrolytes dissolved in the water. So what I'm going to do now is I'm going to take some salt, which is sodium chloride, and I'm going to place it into this deionized water, which is not deionized now, because as I swirl, the chloride and sodium ions are both being separated by water molecules, and those water molecules, remember, the negative part of the water molecule, the oxygen, that's pulling the sodium ions into solution and surrounding them. And the hydrogen atoms on the water molecules, which are positively charged, those are coaxing the chloride ions into solution, and those chloride ions are surrounded, and I can't see the solid anymore. But it's in here. Here's some evidence. So what we see here is that the sodium chloride, when it's dissolved in water, those ions are free to move, flow about in the liquid, and because of that, it allows a current to pass between these two electrodes, making the buzzer beep. And so sodium chloride is an electrolyte. Okay, let me do a couple other experiments here just to show you these properties of electrolytes and non-electrolytes. We're going to take different types of water. So I've got some Aquafina, and I've got some Evian water, natural spring water. This is purified water that then has calcium chloride and sodium bicarbonate and magnesium sulfate added to the purified water. So here we go. I'll take my deionized water, pour it in here. I'll take my Aquafina. It says pure water, perfect taste, purified drinking water. I'll take my Evian water, which is says it's got dissolved minerals in it, calcium and magnesium. So there's probably some dissolved minerals which are going to have some ions dissolved in the water. And then this is purified water that has had some ions added back. I'll just leave these bottles behind each one so that we can give a listen. Deionized water, Aquafina, Evian water, and what's this? Nestle water. It's been purified but had some ions or some salts added back. So we'll go one more time. Distilled water, Aquafina, Evian water, natural spring water, so some minerals are going to dissolve in the water, and Nestle water that's been purified but has had some minerals added back. So that's all an electrolyte is. Salt's an electrolyte. If you add a little bit of salt to water, you've got an electrolyte dissolved in the water. The electrolytes can be divided into two different types. And those two different types of electrolytes are called strong electrolytes and weak electrolytes. So let's differentiate between those two. A strong electrolyte when it dissolves in water, whatever dissolves completely dissociates or completely splits apart into its constituent ions, the ions that make it up. So a strong electrolyte is like sodium chloride, so I'll draw this, sodium chloride, that's symbolizing a piece of salt. When that dissolves in water, we can symbolize that by writing NaCl aqueous, like this. This means the sodium chloride has been dissolved. But it's important to note that when the strong electrolyte sodium chloride dissolves, there's no sodium and chloride ions that are still stuck together in the solution. All of them have separated. All of them separate and form dissolved individual ions. And so really, what's actually happening when sodium chloride dissolves is the ions are split into individual aqueous dissolved sodium ions and individual aqueous dissolved chloride ions, and we'll represent that with this type of symbolism here, that the ions have completely dissociated. That would be the case in a strong electrolyte. In a weak electrolyte, not all of the substance that dissolves dissociates. So acetic acid is a weak electrolyte. So in this case, I'm gonna write acetic acid happens to be a liquid. So I'm gonna write CH2H3O2. That's the formula for acetic acid, which is a liquid. When that dissolves in water, we can write HC2H3O2 aqueous. And in this case, some of the substance that dissolves stays intact in its molecular form, dissolved, but some of this actually dissociates into ions. And we designate this partial dissociation with a double arrow. And we'll write H plus aqueous plus C2H3O2 aqueous. So this designates that while this particular compound has dissolved in water, it's aqueous, some of the dissolved compound dissociates or splits into individual protons that are dissolved and individual acetate ions that are also dissolved. Now what actually happens in solution is that some of these dissociated ions, they recombine and they make the intact molecule. But at the same time, some of the intact molecule dissociates and forms the individual ions. And this reaction happens in both directions simultaneously when you dissolve acetic acid in water. And when those two rates equal, the rate of dissociation and the rate of association, when those two equal, you reach some sort of balance. You reach some sort of level of a certain amount of this and a certain amount of these two things, you reach a particular ratio. And that's what happens in a weak electrolyte. So I'm going to take a little bit of vinegar, which is a weak electrolyte. Sorry, vinegar is not a weak electrolyte. Acetic acid is a weak electrolyte. And vinegar contains 5% acetic acid. So this is an appropriate way to symbolize what's in this jug. About 5 grams of this acid for every 95 grams of water in this jug. Now some of this acetic acid dissociates and forms ions that should be able to conduct electricity. Sure enough. So vinegar is going to be a weak electrolyte because in this sample of vinegar we have some undissociated ions and we have some full acetic acid molecules at the same time.